To start with, a very warm welcome to you all, to University College Cork and to Ireland. My name is Paul Callanan. I'm one of the two co-chairs of the Science Organising Committee, along with my colleague Matt Redmond behind me here. And I'm just going to say one or two very brief words before we open out the opening ceremony to some of our distinguished colleagues on the table behind me here. As Gaeilge for a minute is more an anam dom a bheith an seochanis agus an fáilte a chur rót galéir chun an cruinniú seo in Oscail na Gaillimhe, Oscail na Corcaig. Any of you who know a bit of Irish know that I got things slightly confused with another rival institution. So we're very lucky here this morning to, as I said, have some very distinguished guests here to welcome you all and to formally open the meeting. To my left immediately here is Professor Donna Halloran, who is the President of University College Cork. We're particularly happy to have the Minister for Higher Education, Research, Innovation and Science, James Lawless TD. We're very honoured to have the relatively newly inaugurated Mayor of Cork, Mr. Fergal Dennehy. You're very welcome. Beside him, of course, is the President of the EAS, Professor Sarah Lucatello. Beside her is the head of the College of Science and Technology and Food Science and Engineering here, Professor Sarah Cullity. Beside her, then, we have Mark Kennedy, Matt Redmond, who I mentioned earlier. Mark is very much on my mind at the moment. I'm skipping some people at the very end of the table there, who's played an absolutely key role in the logistical organisation of the meeting here as well. And without him, very little would have happened here, certainly in time for the meeting today. And then between Matt and Mark, there are two vice presidents of the European Astronomical Society here as well. So I won't say any more than that at the moment, except I'm just delighted now to welcome the President of University College Cork here to welcome you all and open the meeting. Thank you.
Good Paul, a Lord Mayor, a Minister, Ara Uachtaráin. Ladies and gentlemen, the warmest welcome to University College Cork. It's an absolute delight to be here. The Minister and I walked in and the Minister said, this reminds me of my classrooms in Trinity College when I came in, when lecture halls were full, as opposed to being the hybrid world that we're in today. So I want to extend the warmest welcome to each and every one of you, wherever you've travelled from across the world, because this is a really special day for the university and for the city and for the country. Really important that we bring colleagues together to learn, to share, and also to inspire each other. I've just come back from Nice myself, where I was speaking at an international conference on sustainability, where I had the privilege of picking up an award for this university to be ranked number 4th in the world for sustainability. And something we're really proud of as an institution, and we work hard at it every day. We're not perfect, but we work hard at it. Welcome to our beautiful historic campus here in the heart of the city of Cork. And the Lord Mayor, congratulations, you were elected Mayor on Thursday or Friday? Friday. So a shiny Lord Mayor. So we wish a round of applause for Lord Mayor, because really important role. There's over 1,500 attendees, so we've got the 4 Bull complex here, and I'll come to Bull in a moment. 77 different scientific sessions, 1,200 oral talks, and more than 1,000 posters. It's the largest conference ever the city has hosted. Okay, so you're part of history of this city and university. Speaking of the importance of your work, and I say this as a scientist, I've had the privilege of working with Professor Paul Callanan for a considerable period of time, and he's an extraordinarily talented person. And okay, we do the work in the laboratory, we do our teaching, we do all that really important work. But I'm going to briefly tell you a story where I was in a dark sky region in South Kerry on the Evora Peninsula, which is a United Nations designated dark sky, where you see extraordinary vision of the sky. And it was a special event that Paul had been responsible for organising. And there were a group of young people along the shores and up on the sand dunes looking at the sky. And you know, in that moment when it's just twilight, and I could just see two children, probably aged 7 and 8, looking into a microscope, or a telescope. All right. Looking into a telescope. I'm just making sure you're all awake. It's all right. And I heard one say to the other, look at the Orion, look at the nebula. And then the conversation shifted. I could hear them speaking. And the young other 8-year-old said to the 9-year-old, said, you know, there are earthquakes in San Francisco. And I just stopped for a moment and I said, here are two incredibly young, talented people who were not concerned about WeChat, Snapchat, or whatever you're having yourself chat. They were much more interested in the natural world because of the inspiration of people like Paul, and I'm sure many of you, who are pointing out the really important attributes of the fantastic globe that we live in. And I don't know if you've read the book Orbital, which won the Booker Prize last year. If you haven't read it, it's worth a read. And it's a story of the astronauts in the space station. And as they passed around, they did 14 cycles of the Earth every 24 hours by their clock. And it's just extraordinary from someone like me to be inspired by the work that you do. So whether that's that young person, those young people who have changed their lives, Paul, and the work that you have done, and many of you here, but also every bit of work that you do every single day. This university is celebrating 180 years this year. We built this university in 1845. If you know anything about the history of Ireland, Ireland had a famine in 1845. Our population was 8 million. The population was halved between immigration and debt. We built the university during that time. 5 years after we started putting the first blocks down, the first groups of students arrived, 115 students, all men. The first student was soon to be the son of the professor of surgery. The next student came from Lincolnshire. And we believe the reason they came from Lincolnshire is they've been inspired by our first professor of mathematics, which was George Boole, after whom this complex is named after. And you will be familiar with, I hope, with George Boole, Boolean logic, written a booklet for the laws of thought, about a kilometre from here, where it exchanged the world for all of us. And that pride we take to today, to the university today, which has got 26,000 students, 61% female, and 5,000 international students from 124 countries. That's the milieu that you're in today, and that you're adding to the extraordinary talent that we have in this institution. Ireland has a long history of astronomy, stretching back to Newgrange and the alignment of stone circles to be seen all around Ireland. The observatories built in the 18th and 19th century, including our own beautiful Crawford Observatory, which is up there, I think, Paul, isn't it? Yeah. This is located right on our campus grounds and is home to instruments built by the pioneering astronomical technology in the 19th century, Howard Grubb. We are incredibly proud of our astronomical heritage here at University College Cork. Records of astronomical observatories in Cork date back to 1770s and have been important for the measure of precise longitude and latitude of Cork, contributing to the first accurate maps of these islands. Irish astrology today is thriving, supported by the membership of the European Space Agency since 1975, and more recently the European Southern Observatory in 2018. And Ireland's membership of these intergovernment agencies is a significant boost to astronomical research, resulting in strong expansion of research capacity and scientific ambition, the benefit of every university in Ireland, including University College Cork. And I want to acknowledge our Minister and his support for much of that momentum behind securing the resources that are necessary to do that. Astronomy plays a key role in attracting young students to STEM. I don't know if you know that Ireland has the highest number of students that are in third level education in the OECD. 40% of the graduates of this system in Ireland are STEM graduates. It's the highest number of STEM graduates per capita in the European Union. So we're really proud as a community for what we're seeking to do here. This event is all about sharing knowledge and building lasting connections, and I encourage you to listen actively and make time to connect and share experiences. Can I also make a special plea to those of you who might have grey hair like me, or perhaps no hair at all? And my plea is that there are early career researchers here today who will be listening and observing in awe of many of the people that are over in the front row here and many in the audience who are keynote speakers. please put the ladder down to those early career researchers, because we were all young at some stage. We all need to be encouraged. Please encourage them in conversations, because they're in awe of the work that you do. But they are the future, many of these early career researchers. So I ask you maybe perhaps to reach down to those as you walk around our beautiful campus through the sessions and between sessions. Finally, I would like to thank everyone of my colleagues in UCC who made this possible. Professor Callan himself, Paul, has been championing this for a considerable period of time and is head of the local organising committee. Dr. Mark Kennedy, and I've known Mark a long time, he's an extraordinarily credible, talented physicist as well as an incredible organiser. And also like to thank Professor Matt Redmond, and I think this is where Paul got confused that he was in Cork or Galway, because Mark is the School of Physics at the University of Galway. Mark, great, and thank you as the Irish representative of the European Astronomical Society. But I want to particularly welcome Professor Sarah Lucalo. Sarah, as President, thank you so much for being here, giving us the opportunity to host this here in University College Cork, and we hope that you have a wonderful time in our beautiful campus, the wider Cork region, and have a very productive meeting. Now, it just remains for me to do is to introduce our Minister. So thank you, and I wish you well. Gomila Mahagov. So it's my privilege now to introduce our Minister, excuse me, Minister James Lawless, Minister for Further and Higher Education, Research, Innovation and Science. Minister Lawless was elected to our Parliament to represent the Kildare North in 2016, 2020, 2024. Before that, he served in local government and was appointed Minister for Further and Higher Education in January of this year. And I can tell you across the entire sector of higher education in this country, people were absolutely delighted that this minister was appointed to this role. Because he's been a very strong voice of technology, digital policy, introducing groundbreaking legislation and social media regulations. His passion for learning, his passions for knowledge are obvious to anybody who's met him. The Minister has studied mathematics and computer science at Trinity College in Dublin. We forgive you for that, Minister. You probably should have gone to UCC, but we let you off for that. And then, of course, he took his barrister examination at the law at the King's Inn in law, where he is now a qualified barrister also. He's originally from Wexford, has spent many summers growing up working in the local tourist and hospitality industry. But luckily for us, the Minister is absolutely passionate about higher education, research, and focus on the future, in securing our future for a great country for that this country is today. And I'm really proud to introduce our Minister, Minister Lawless. Thank you very much, everybody.
Go raibh mágad Uachtarán ó Halloran, Máidir a cóide, churann sé an áthas orm a bheith anseo inniu chun an códáil seo a oscailt go hoifigúil. Good morning, delegates, and for the non-native speakers amongst us, a broad welcome to all of you who have travelled far and near to be with us for the 2025 meeting of the European Astronomical Society, and I want to welcome you to Cork for this event. Mayor Dennehy, we're very privileged to have the Mayor, and probably what must be one of his first official roles, having been newly minted and elected to that august office on Friday, and I want to congratulate him wholeheartedly. I know he'll do the state some service, and indeed the city indeed as well. President O'Halloran, for your leadership and for opening today and for leading this institution on every day of the year, and Professor Callanan for organising and putting this together as well. I want to join in the welcomes to Professor Lucatello, President of the European Astronomical Society, to welcome you to Cork, Professor, and acknowledge the Society's excellent work of building international networks to advance astronomy. And to welcome all of you here as delegates, as observers, as participants, as people with an interest, a shared interest in the area. And I hope you have a productive and useful conference, and I'm sure you will. And I want to thank the hosting committee for the work in organising the conference, which, as we've just heard, is the largest ever organised in Ireland, so making waves again. And I can see, and I did remark to the President coming into the hall, that is the first time in many years that I've seen a full lecture theatre. I think even sometimes on Friday mornings, even before, they weren't always full, even before hybrid, but it's actually great to see so many people gathered physically in a room about to share knowledge, share conversations, learn from each other, and engage in science and the discipline that goes with it. So great to see it, and also to acknowledge Dr. Kennedy and Professor Redman, along with Professor Callanan, who all played a major part in pulling this together. And the conference stands as a celebration of research excellence, scientific discovery, and shared ambition, and it provides a platform to exchange the latest research, to reflect on progress and to shape the future of astronomy in Europe. And perhaps looking a little bit further afield than Europe, looking to the wider horizon, we are at a time of uncertain geopolitical change, global headwinds bringing not necessarily trade winds, but bringing us other directions and uncertain futures. And it is a time of instability, which is hugely concerning. So if we think about the words from the Prophet Muhammad, he said, "The sky is a shared roof for all of humanity. It does not distinguish between race and religion. It belongs equally to us all." So I think that concept of a shared sky is one that as astronomers and as politicians and as human beings, I think that we can speak to and resonate with us, and certainly it resonates with me, that concept of that shared sky, because it is both our object of study for the field that we are engaged in today, and a reminder of what connects us beyond borders, and our curiosity and our responsibility to each other. So I think that that shared sky is a metaphor for all that's good about science and all that's good about astronomy in particular, but bringing us together, in a borderless way to engage on all that is best of us as a human race and us as scientists. And of course, we are gathered in Cork today, the centre of European astronomy for this week at least, maybe other weeks I'm sure as well, but certainly today. And Ireland has a long tradition of astronomy, which continues in our European collaborations. And this week's gathering of almost 2,000 astronomers between the people in the room next door and online. And we have, as the President mentioned, a long tradition of studying the skies. 5,000 years ago, our ancient ancestors built monuments like Newgrange, which tracked the winter solstice, most famously with the rays penetrating to the chamber on the shortest day of the year. And of course, we've only just come from the longest day of the year being on Saturday, being the summer solstice. And we have the tradition in Ireland as well of the Beltina, the bright fire, which burns and typically was in the run into the summer solstice. We would celebrate the harvest and the beginning of the yield and the ripe, rich crops. And many, many cultures and many, many societies have had equivalent traditions. But those festivals, those looking for the longest day, those solstices, again, have often tracked around the tides or on the moon or in the stars or in the sky. And natural phenomenon which impacts upon the ground is manifest in the sky. And that's what we do in this discipline to understand what's happening in the skies above us and why it is so. And I often think, even though I work with all the time, and particularly privileged to do so in this role, the greatest and latest equipment and some really extraordinary things like the LOFAR telescope and the SKA array and other technological advances that I'm hoping to support more and more of as minister, to be able to fund and to support Ireland taking its place amongst the nations of the world. We've already joined the likes of ESO, etc., but there's more to come. But I also think about people like Ptolemy, in the 2nd century, Greek astronomer, going out into the sands and putting sticks on the ground and studying the movement of the sun and the shadows that fell from it. And 1,500 years before most of the planet realized it wasn't a flat Earth, he was able to predict the circumference of the globe pretty accurately with nothing other than a stick and a shadow and a pen and paper. Not even a pen, probably a pencil at the time. So it really goes to show that curiosity is really such an important motivator, and people that go out and do their own research. Fundamental research is such an important part of this. Without any preordained destination or preordained impact study, a return on investment or anything like that, that go out and study and examine and are curious, will produce excellent results, which will of course have impact later on. So I think that's a really important lesson as well. I suppose looking back closer to home, Sir William Rowan Hamilton, and I in Cork, perhaps I should apologise for being a Trinity student, but Hamilton gave his name to one of the institutes that I studied in, the Hamilton Institute in Trinity. But Hamilton did many, many things, of course. And one of the things he was closest to was the Dunsink Observatory in Dublin. And from 1845 to 1917, Ireland had the largest telescope in the world, the Leviathan telescope at Birr Castle, which was linked. And of course, there's another observatory in the college here that I've just had the chance to see as I came through this morning. So Ireland has been leading through centuries of these sort of observatories, these sort of telescopes of different degrees of maturity, and leading the way on that. And recently, the historical astronomical observations of Ireland were added to the UNESCO World Heritage tentative list in recognition of their importance. So the list, sort of the waiting room to get into the UNESCO heritage status, but only right that should be the case, because places like Dunsink, places like Birr, indeed the observatory here, are all recognition of the standards, the high standards in the pursuit of excellence and the pursuit of curiosity that we were striving towards as a nation for many, many centuries. We have, I mentioned already, the Lowfar Station now in the grounds of Burke Castle and preparing for the Lowfar 2.0 upgrade beside the historic Leviathan telescope. So it's a wonderful marriage of old and new. So we have the earlier telescopes, which for many years was actually the greatest of its kind in the world, and now in the same site since the Lowfar telescope about to be upgraded. And that's a great story of the journey from past to present to future. And they all sit side by side, and that legacy continues as Irish researchers now work on those cutting-edge discoveries with colleagues from across Europe and indeed beyond. And this week, on Tuesday last, I visited DIAS, the Dublin Institute for Advanced Studies, to celebrate 85 years of their activity there, a pure research institute, first in Europe and only the second in the world after Princeton, where it is pure research activity. And that includes, of course, the School of Cosmic Physics, and a great many astronomers, I imagine some may well be here today, are participating online. So that endeavour is writ large in Irish science history. And I'm minded as well, continuing, I suppose, the Cork Dublin theme, there was the Sean O'Casey play, perhaps a little bit further from Hamilton, but in Juno and the Paycock, the famous Sean O'Casey, author and dramatist, had a character called Joxer, who may be familiar to some of you. And Joxer was, I think, a Dublin man. A Cork man would have put it far more eloquently. But Joxer asked the question, what is the stars? What is the stars was his way of giving vent, and perhaps in his limited vocabulary or imagination, but he still was able to grasp the concept of this kind of existential confusion and the search for meaning and the search in chaos. So what is the stars is a pretty fundamental premise that we can all ask ourselves as we set ahead upon our journeys, be it philosophically, be it through humanity, and indeed through astronomy. I think that's not a bad, pithy summation. What is the stars? And that is what we're here to answer today as part of our conference. So we have almost 2,000 astronomers for a very ambitious program across the next couple of days. And many of these themes are one in which Irish astronomers have played an important part, supported by our membership of LOFAR, ERIC, the European Space Agency, and the European Southern Observatory. And Irish astronomers are making leaps and bounds in national and international projects as part of the above collaborations and more. Supported by government, and we have commitments in the programme for government to further support all this exploration activity and indeed to continue our international collaborations and indeed expand upon them. And though with those collaborations and with those support, and of course working with the European Space Agency, students at UCD, the Centre for Space Research, designed, built and tested Ireland's first space satellite, AirSat-1, which launched in 2023. We see on radio astronomy, scientists from across Ireland are using LOFAR to work on pulsars and space weather. Researchers in the Technological University of the Shannon are using expertise in machine learning and computer vision to study solar weather. And I was honoured to witness an agreement, a memorandum of understanding between TUS and DIAS last week, where the high performance computing and AI machine learning capacity of TUS was put with the accomplished and established space weather expertise of DIAS to pull the two together, to take the data, take the analytics, and actually collaborate on how they drive that forward. I think that is very much a pattern that we'll see in future as institutions grapple with the large equipment and demands needed to do really advanced research, that those kind of cross-institutional collaborations bring the best of both together. And sometimes in unexpected ways, because science takes many paths, many directions, and the analytical requirements to take a set of data may not map exactly to the disciplines that actually procure that data. So that kind of collaboration, I think, will be a feature of science going forward. We see too in Trinity, researchers received a European Research Council grant to use the ESO's very large telescope for the Cosmic Leap project. That will map the depths of white dwarf stars. And Ireland has reason to be proud of our existing scientific performance on an international scale. And as a minister, supporting this success, driving it on, and driving it to further ambitions is a major priority for me as minister. It is so important that we continue to support wholeheartedly fundamental science, basic research, blue sky research in every sense today, because that is the foundation for the technologies of tomorrow. That is the inspiration for the students of today, and it is a beacon for international collaboration. And we'll never have applied science if we don't have fundamental science, because you have to start at TRL 0 to get to TRL 10. You can't just make a product development from scratch. It is all the pipeline of blue sky research and foundational thinking that actually gets us up the TRL chain into economic impact and so forth, which is incredibly important, but you won't have one without the other. And I think they are equally important and need to be equally resourced in that way. This week, I imagine you will share and celebrate exploration and discovery, learning from what we know and prepare for those discoveries to come, learning from what we know and trying to understand what it is that we don't know and how can we get there. And this is a pivotal time for European astronomy. For many reasons, if we look at space, we have many orbiting observatories, the James Webb Space Telescope, which continue to revolutionize our understanding of multiple areas of astrophysics research. And I'm proud to say that there are technologies and instruments on the James Webb Space Telescope developed by Irish companies and researchers. On the ground, the European Southern Observatory and LOFAR continue to drive the cutting-edge instrumentation and telescopes which drive the scientific ambition of the European astronomical community onto further scientific discovery. And looking to the future, the development of revolutionary ground-based facilities such as SKAO, CTAO, the ESO's extremely large telescope will all open new vistas for European astronomy. This is a time for major development when it comes to the advancement and proliferation of observational facilities. And for the ELT, the Extremely Large Telescope, I'm happy to note scientists at the University of Galway are currently working with colleagues across France and Italy to build a Morpheo instrument, and Morpheo will play a key role in that Extremely Large Telescope achieving sharp imaging from the ground. European astrophysicists will further benefit from upcoming space missions such as Plato and Ariel, not to mention the even more ambitious missions planned for the next decade. Across all of this understanding of the universe as it evolves, the observations we need to underpin this knowledge will require cutting-edge engineering and technology solutions, because we have, as I said, so many fields contributing to this shared endeavour, and we have data gathered, we have exploration, we have new boundaries, and then we have parsing and analysing of that data and pattern prediction from it. So I look at the contributions Ireland can make to build on our success with the James Webb Space Telescope and others. And of course, that needs human talent and ingenuity to drive the science and develop the associated technologies. And I would like to acknowledge the success of the many astrophysics degree programs in Ireland, which attracted students to STEM-related courses, many of which go on to work in other areas of research or indeed in industry. Astronomy has enormous power to spark scientific curiosity, connecting children to look to their first telescope to researchers modelling the first moments after the Big Bang. But it is not only the moment of inspiration that matters, it is the facilitation of continued learning and curiosity at all levels, from the earliest school years right through to postdoctorate level and beyond. Building those skills, building that pipeline, facilitating those researchers to continue that journey and to collaborate at the highest levels is core to my work as Minister. And the success of European astronomy is built on our collective ability to harness the ingenuity and skills of the entire European community, requiring strategic forward planning driven by scientific ambition. And in terms of that forward-looking approach, I know you'll be discussing this week what is next for European astronomy from 2040 beyond. And it is the first time, I think, that we have looked at that question with such a broad scientific community and expert community and look beyond to see what is next. And of particular note will be the ESO's Expanding Horizons programme, which aims to develop the next transformational facility that will advance humanity's understanding of the universe whilst fostering international collaboration. The Senior Science Committee overseeing that process, which will make scientific recommendations, is chaired by our own host today, our UCC astronomer, Professor Paul Callanan. So the future is in safe hands, and that task is part of the work we start today, to consider how we can work together internationally, how we can advance humanity's understanding and advance the universe and our understanding of it. And I'm proud of course, our role in the astronomical advances of the past, present and future, but we need to look to where we go next and what is next and how we can harness it. So we are at a point in astronomy where our biggest advances will not be made by any one country. I mentioned that any one institution is challenged, but collaborating together on a country-to-country, institution-to-institution basis, I think, is the platform on which we will leverage discoveries and look to the next generation. Astronomy is by now, by necessity, an international endeavour due to the scale of the facilities. Science, and particularly astronomy, has an immense power to bring people together over the most fundamental questions about the world around us. International cooperation in research and innovation brings together people from across the globe to understand our universe through exploration, fundamental research activity, and scientific excellence. And as we look towards the future of European astronomy, our success will depend on both technical excellence and the strength of our international partnerships. And I quoted the prophet at the start of it, and to look to Kofi Annan, our United Nations leader for many years. He said, we all share the same sky, the same air, the same hopes for our children's futures. So returning to that concept, it is the shared sky. What is the stars? The stars is all of us, and the stars is our shared future, our shared present. And that spirit of openness and working together is as important now as it has ever been, more important than ever, I would say. And it is inspiring to see astronomers coming together from Ireland, from across Europe, and across the globe to consider what comes next. The future of European astronomy is a shared project, one that must be, and by definition I think will be, ambitious, collaborative, sustainable, and that asks what's next, and asks what is the stars, and asks what is it above our shared sky. So I'm particularly proud to open EAS 2025 in Cork this morning, to wish you every success in your endeavours, personally, professionally, academically, in learning and forging new relationships and further collaborations. The future is in good hands, and I hope you have a very productive, successful conference. Thank you.
So thank you very much for that, Minister. The President and the Mayor have to leave now. I think, Minister, you can probably stay maybe for just one more minute.
That's what I'm told. You can see who's in charge.
Yes. And now, just to finish the event for this morning, it's my pleasure to introduce to you the President of the EAS, Professor Sarah Lutatello, to welcome you all on behalf of the EAS.
Thank you, Paul. Kharja is more an honordam ave ansha Igor Kag. I tried. Dear participants, colleagues, and friends, it is a great pleasure to be here with you in Cork in this beautiful campus. I've never been here before, but I'm thrilled to have such a beautiful location for a meeting. Let me start by extending a warm welcome to all of you to the annual meeting of the European Astronomical Society, and a very special thank you to the distinguished authorities that were in attendance today. The Minister for Further and Higher Education, Research, Innovation and Science, James Lawless, the Lord Mayor of the City of Cork, Fergal Dennehy, and the President of the University College Cork, John Halloran, who had to leave because we were running late, but we very much appreciate your gracious hospitality, and we're very honored by your presence at our opening. It's a delight to hold our meeting here in Cork for the first time in Ireland and experience the hospitality and energy of this wonderful country. The Irish Astronomical Society has been growing and thriving in the last decades. And this week, thanks to EAS 2025, it is the world capital of astronomy. I'd like to thank all of those who worked tirelessly to make this happen. It's a big job to organize a meeting like this, truly a big job. So, first of all, the annual meeting board led by Vice President Lex Capper, the Scientific Organizing Committee, which was led by Paul Callanan and Matt Redman, and of course, the local hosting committee, led by Mark Kennedy and Michael Trammell, who have done a tremendous job. Big thank to them. Kwoni Tumlara, who's our partner to make everything work. And last but very much not least, the over 70 volunteers in the bright green shirts who will be making sure throughout the week that everything goes smoothly. We owe you a huge thank you. So the president of UCC already shared a few numbers that give a sense of the size and richness of this meeting. What I'd like to add is that beyond the 1,500 people here physically in Cork, we're joined remotely by over 700 participants. This year, plenaries, symposiums, selected special sessions are offered and available online, are offered hybrid, and this is a testament to our commitment to making the meeting more accessible. One number we're particularly proud of is roughly 1/4 of the attendees here are students, and about half are early career researchers. This is a vital sign of the health and future of the European community. And a particularly important fact to highlight, I'd like to share with you, is that 1 in 8 participants have received some form of support from the society to attend the meeting. We commit a fair amount of resources every year to enable that. And thanks to the generosity of two of our organizational members, the Merak Foundation and Springer, we have been able to increase the support and enable even more colleagues, especially early career researchers, to take part in our meetings. To the young people, to the early career researchers and students here, I have a few words for you. I invite you to take advantage of this meeting to build connection, to share your work and ask questions and speak up. Do not hesitate. This is how your science grows, and this is how our community grows. Many of you will be giving the first talks in a big conference this week. You probably are a little nervous. I think that's perfectly normal. I know I was the first time it happened to me. And this is the first time I opened this meeting. So I'm a little nervous as well, but I trust that I'm among friends. And this is true for you too. So don't worry too much. You'll be fine. Science is a powerful tool to build bridges between people across borders through time. Every collaboration, every mentorship and relationship is an act of connection. Science is a peaceful exchange of knowledge, and we believe in fostering an environment where researchers from all backgrounds can cooperate and work together peacefully and respectfully. Holding this value at heart is particularly important today as the world is shaken by numerous conflicts, and we stand in solidarity with the too many colleagues whose lives have been affected and are affected by war. Now turning to the society itself, the EAS continues to grow. We now have more than 5,400 members. If you're not yet a member, please consider joining. If you're a member of one of our affiliated societies, joining for you is completely free. All you have to do is to get in touch with affiliated society and learn how you should, what kind of paperwork or box you have to tick to become a member of the EAS. If you're a member, the General Assembly will be held on Wednesday at 12 noon. This is your opportunity to learn about our activities, to ask questions, and provide your feedback. I encourage you to join us there. If you're not a member, you're welcome to attend and listen. And maybe you're considering to become a member and learn about it, so please come and listen in. Over the past years, we've seen some changes in the council. We bid farewell to Jarle Brinkman, who stepped down. Jarle has been a thoughtful and wise voice in council, and his contribution has been precious to us and to our work. While we will miss him, we look forward to continuing to work with him in his new capacity as EAS Director for Science. We're very pleased to welcome Robert Massey as the new council member. Robert brings tremendous experience both in science and science policy, and we're lucky to have him join our leadership team. We also welcome two new organizational members this year. JIVE, the Joint Institute for VLBI ERIC, and the Europlanet Society. We greatly appreciate your support. The involvement of our organizational members strengthens our goals and increases our capacity to work together towards shared goals. I invite similarly minded institutes and organizations to consider joining the EAS in this capacity. We'd like to warmly thank the Wilhelm and Else Harris Foundation for their continued support of the Harris School Series, which provides valuable training opportunities for young astrophysicists. Following the successful editions in Garching and Athens, the next school will take place in Pisa later this year. The applications are still open until June 30th. If you're an early career researcher, I urge you to consider applying. This is a great opportunity, especially because the foundation generally covers all local expenses for attendees. And furthermore, they have committed funding to support travel for early career researchers from Ukraine. We're also pleased to announce that the foundation has committed to fund the school for additional 3 years, which ensure the continuation of this important initiative. The EAS continues to be committed to its advocacy efforts. The protection of the dark and quiet sky is still very much one of our priorities. We're active at the international level, at the UN Committee for the Peaceful Use of Outer Space, and with regular interactions with the EU commissions. We also work more closely with our affiliated societies to build stronger national level advocacy. The Council is preparing for another event at the European Parliament early next year, building on the success of two previous engagements, which happened in 2019 on the topic of Gaia and 2023 on extrasolar planets. The forthcoming event will highlight the critical role of major upcoming European grant-based facilities in maintaining and advancing Europe competitiveness in astronomy. It will also provide a platform to raise awareness on some key issues, like, in fact, the protection of the dark and quiet sky, and reinforce the importance of continued investment in research infrastructure and international collaboration. To support an informed advocacy effort, the EAS has established EAS Policy Advisory Group, EPAG for short, which provides expert advice and engagement with European institutions and the broader policy ecosystem. The EAS is also introducing the EAS Fellows program, starting early next year. This new initiative will allow us to recognize members who have made outstanding contribution to European astronomy, not only necessarily through science, but also through outreach, through contribution to the society itself and service to the community. It will complement the roster of existing prizes and strengthen our bond between the EAS and its membership. More information will appear on the website soon, so stay tuned. We're also drafting a current first strategic plan for the society. The document, which we expect will be finalized sometimes early next year and in collaboration with the affiliated societies, will outline our plans for the upcoming decades and for the upcoming decade on priorities and actions. One of the key objectives is to ensure that the voice of our members is heard in shaping the future of European astronomy. As part of this effort, we're facilitating a dedicated symposium, which will take place on Wednesday, to explore upcoming flagship projects and reflect on the long-term scientific and strategic landscape. Let me close by saying, this meeting is a celebration of science, a community of curiosity. Whether you're an established scientist with hundreds of talks under your belt, or a PhD student giving your very first one, we're all here for the same reason, to share knowledge. So enjoy the talks, enjoy the collaboration, the chats, enjoy Cork, and have a wonderful EAS 2025. Thank you.
So that is the finish now of our opening ceremony. I think we'll return to normal broadcasting and the plenary session in a few minutes. But thank you all for attending and tuning in again.
I didn't shoot anybody. Okay, so now the official part is open. Let's get back to science. It's my pleasure to present the first award of the European Astronomical Society for this year. This is the Ludwig Vulture Lecture for 2025, which is awarded to Professor Jürgen Christensen Dalsgaard for his pioneering work and impact in the fields of helio and astroseismology.
Thank you for this very, very great honor to be invited to present the Vulture lecture of this wonderful meeting. It's also my first time in Cork and my first time in Ireland, and I've enjoyed it very much so far. I should also say that I have not had much connection with Professor Vulture, but I met him on a couple of occasions, and I'll get back to that later. So, and then I need to figure out how to work this. Yes, that works. What I really want to start with is to say that we have a golden anniversary this year. We have two golden anniversaries. The second one is my marriage, which we're going to celebrate in a month. You have to congratulate my wife for sticking it out so long. But the first anniversary is the start of helioseismology. And that really started with these observations made by Franz Ludwig Deutner, who showed for the first time standing waves in the sun. The 5-minute oscillations had been known for about a decade, but it was only through these observations that Deutner was able to show that the power in the oscillations were concentrated in ridges corresponding to standing modes in the solar interior. So these are waves of fairly short horizontal wavelengths, fairly high wave number, and frequencies periods around 5 minutes. And so this was really the start of learning about the solar interior from seismic techniques. The next step, which followed quite shortly after, was observations from the South Pole, made by Eric Fossat and Pomerantz and Gregg, observing the sun as a star, and again showing a power spectrum, but now just power as a function of frequency, and showing this very rich forest of modes in the sun. Each of these peaks is a normal mode of the solar interior. These are acoustic waves penetrating, in this case, all the way to the center of the sun, and so they provide information about the whole solar interior structure. And this kind of data is something I'm going to return to repeatedly, also when we move on to astroseismology, to seismology of other stars, because that is what we are able to observe there. For the sun, we can observe the solar surface in detail, and so we can observe the modes as a function of position on the solar surface. But these very early observations that really started a huge development in techniques, development of instruments, and but before I get onto that, let me just summarize what we're looking at. We're looking at waves on the solar surface, stellar surfaces, and each mode is characterized by a spherical harmonic, and so by 2 wave numbers at degree L, counting the number of nodal lines on the surface, 1 in this case, 2 in this case, 3, you can't see it quite in this case. And then a number m characterizes the number of nodes around the equator. And in the sun, as I said, we see modes all the way up to very high degree, much beyond this degree of 20. When we look at in the interior of the sun, what we then see are sound waves propagating from the surface where the modes are excited by turbulence. In some cases, for the very lowest degrees, 0 and 2, all the way into the core. In other cases, for higher degree modes, bouncing around in the solar interior, penetrating to different depths into the sun. And having these modes at different penetration depths actually allows us to peel off the different layers of the sun and measure properties, and especially the sound speed in the solar interior. So the result of this development of techniques were various both ground-based and space-based missions, and very importantly, the SOHO mission launched by the European Space Agency together with NASA, and making very high degree, resolution observations of the solar surface, and essentially repeating Deutner's observations, but extending in wave number all the way from degree 0 to 200. Deutner would have been up here. And then in frequency from about 1,000 to 4,000 microhertz, with the 5-minute oscillations being in the middle here. And again, you see these very different modes with frequency depending on degree. And these are the observed modes from even fairly early observations. And they're plotted with 1,000 sigma error bars. And these frequencies are known with a precision of 1 part in a million. They're known better than we know the gravitational constants. And then we can compare that with the models of the sun. This happens to be my best model. And just looking at this, you'd say, okay, we're done. It all works. The model is a perfect match. But then you start to look a little bit more carefully and see there's small departures. And that, of course, is where the interest really lies, to understand those departures. And one early example of that, and that is where I get back to my connection with Professor Volcher. He was the first editor of the Astronomy and Astrophysics Review, and he invited Werner Deppen and me to write a review on heliocosmology and the equation of states. And what we showed there, these were very early data, where we did what one should do in this case. We should take the observed frequencies and then subtract the model frequencies and see how well the model fits the observations. And so here's one fairly early model. And what you see are the differences are, you could say they're small. They are of the order of a few 10, 20 microhertz out of 2,000 microhertz, so of the order of 1%. You can also see the differences are very systematic. They increase with, they vary with the degree of the mode, they vary with the frequency, and they are quite scattered. And one result that we showed in this analysis was that if you, that's the case for this very early model with very simple physics. And what we then did was to upgrade the equation of states, the relation between the pressure and temperature and density of the matter in the model, by including the Coulomb effect between the different components. I mean, the matter in the sun are charged particles, ionized atoms, nuclei, ionized atoms, and electrons, so there is Coulomb interaction. It's a weak effect that's normally often neglected in stellar modeling. But when we included that, all these curves collapsed into one single behavior, which it turns out showed us that the model is a much better representation of the solar interior. So that's the first example of learning about the physics of stellar interiors from these data. And that then goes on, and because we have so very detailed data, we can use the data to measure the sound speed in the solar interior and determine the difference between the sound speed in the sun and the sound speed in the model. These are relative differences. The differences are less than 0.5% in the square of the sound speeds. This again is a much upgraded version of my model, and what we've done here, you should realize, is that we predicted the structure of the solar interior to a precision of 0.5%, based on the physics that we know. This is not a fit to the data. This is a model prediction, and then compared with the sun, and showing that the model is not so bad, but also showing that the model is terrible. Because what we have here, again, are error bars. You can't see them. They're smaller than simple size. And so the model differs from the observations by much, much more than the precision of the observations. So we have to do more. So we did more, and one of the things we did was to improve the determination of the solar composition. And the result of that was that things got worse. This is the model I showed before, and these are models computed with revised measurements of the solar surface abundances. And that's where we are now. That's why we need young people to help us figure out what's wrong with the model. Because we still don't know. Is it the determination of the opacities, which is a tough problem? Is it the determination of the solar composition, which is also a tough problem? Is it just because the model, we don't know how to compute stellar models? And that would be a terrible problem, because all astrophysicists, whether they know it or not, are using stellar models for their research. So if we can't compute a solar model, we are really stuck. So that's where we are with the sun. But let me move on to our stars. And of course, having seen the oscillations in the sun, we knew we should see them also in stars like the sun. And as I said, the oscillations are created by the turbulence, convection, turbulent gas motions at the stellar surface. And we see that in all cool stars. So all cool stars should have oscillations. And the difficulty, the aspera, is that the amplitudes of these oscillations are tiny. A few centimeters per second in velocity, a few parts per million in intensity. And so that meant that it took a long time before we had equipment able to see these oscillations in our stars. And here comes my second connection with Professor Voltier, because he was president of the European Southern Observatory at a time when I was on the Science and Technology Council of ESO. And that was a time when the VLC was being designed and built. And some of the early data that we got on stellar oscillations were actually obtained by using one of the VLC telescopes, an 8-meter telescope, to observe one of the brightest stars in the sky, Alpha Centauri. And that gave us these really very nice data. You remember the spectrum I showed for the sun? This looks very similar. It's a slightly lower frequency. Alpha Centauri is a bigger star. And, but we can do similar kind of analysis as we've done for the sun on these data. And also by showing that using this kind of optimal technology to make the observations inspired my group in Aarhus to think, oh, okay, we can do this with an 8-meter telescope, observing a bright star. But actually the observations only, the telescope was observing for only 1 second, and then downloading the data for 59 seconds. And so if you scale that, you can see that, okay, you can scale that down to a 1-meter telescope, observing all the time, and then you get the same kind of precision. And that then inspired us to start developing the stellar observations network using 1-meter telescopes and with optimized spectrographs to do this kind of observation. We now have a site in Tenerife that's been operating for a decade. We have a site in Mount Kent in Australia. We have a site being tested being commissioned in China. And we have a site being built in New Mexico. And we're still working to find collaborators to produce sites also in Chile and in South Africa. And the idea, again, is to have a network of telescopes to be able to observe stars around the clock, because we need data stretching over many weeks or months, and then to have optimized instruments to be able to do this. And we have actually already observed Alpha Centauri from Australia, in this case with a 70-centimeter telescope, and with data that these are very early data, and we are getting close to the VLC precision that we obtained so many years ago. So this is all very well, but there are so many stars, and we can only observe one star at a time with this network. We need something else, and we have been very fortunate in astroseismology to get the ideal mission for astroseismology being developed by Bill Borucki to look for other planets around other stars. And the point here is that to do that, using his technique, you measure the effect of the planet passing in front of a star, causing a very small dip in the light you measure from the star. When the Earth passes in front of the sun, looked from a distant star, you have a decrease in the light from the sun by about 1 part in 10,000. So you have to be able to make photometric measurements to a precision much better than that. And that's exactly what you need to do astroseismology using observations of stellar luminosity variations. And this is also what Kepler has been doing, in addition to looking for planets around other stars. And Kepler has actually been looking at stars all around over the HR diagram. We have effective temperature here, luminosity here. We have the sun here. So solar-like stars, obviously, red giants, hotter stars, white dwarfs. So we have an extremely rich set of data now on stars, all allowing us to look at the stellar interior and learn about stellar interior physics. And what I'm going to talk about here in the last bit of my talk is just one example of what we've learned from these wonderful data. Namely, staying with solar-like stars in the sense that the oscillations are excited by convection at the stellar surface, but moving from the sun up the red giant branch. So looking at what's going to happen to the sun as it grows really old. But before I do that, let me just show you one example of really solar-like stars observed with Kepler, a binary star 16 Cygni A and B, showing again this power spectrum, showing all the standing waves in the stars, the same structure as we saw from the South Pole for the Sun, but of course with much, much higher precision. These are about a year's worth of observations of these two stars. You can see right away that the frequencies are lower than for the Sun. The stars are bigger. You can also see that this star is bigger than this star. And from this, we've been able to start to measure the age of the star. We've been able to characterize the composition of the star and test our stellar models. And I should mention, since I mentioned Kepler, is that by doing this kind of analysis for stars with exoplanets, we can then also use that characterization of the star to characterize the planetary system. And so we can determine ages of planetary systems found by Kepler and demonstrate that some of these planetary systems are twice as old as the solar system. But let me move on to what I find, from the point of view of stellar science, even more interesting, looking at what happens as the star evolves up the red giant branch. So you all know that in stars on the main sequence, like the Sun, we have hydrogen burning in the core, and that when the hydrogen is used up in the center, we get hydrogen burning in the shell around the helium core. And that evolution causes the star to grow in radius and luminosity, decrease in temperature, so we move up the red giant branch, up to a point where helium ignites in the core of the star. And so we have a helium burning in the very inner part of the star. We still have the hydrogen shell. And the star actually moves down and settles in what we call a red clump, and then move up the asymptotic giant branch, which we'll hear about later this morning. So what happens to the oscillations of the star? Well, the point is that we have these acoustic waves. They're excited by the convection, and we see that in all these stars. But what's happening in the core of the star is that we have the helium core that contracts, becomes very compact. And so at the outer parts of the inner parts of the star, outside the helium core, we have a very high gravitational acceleration. And that means that we get into a point where other modes become relevant. We've been talking about acoustic waves, you all know about that. That's what I'm making right now, talking. But if we look at the Earth's atmosphere, we also have internal gravity waves. You can see that reflected in the bottom of the clouds here, or in the atmospheric radiation here, where you have these waves of different conditions, giving rise to these variations in the radiation. And we also have these waves in stars. And because we have this very compact core, the frequencies of these internal gravity waves in the stars become so high that they interact with the acoustic waves, and we can see them on the stellar surface. And so in these stars, we have two different kinds of waves. We have the behavior, we have acoustic behavior in the outer parts of the star, and we have these gravity waves behavior in the core of the star. And we see that if you look at the frequency spectrum, I'm not going to go into details, but we have these peaks for motion degrees 0 and 2, corresponding to what we see in the sun. But then we also have a group of peaks here corresponding to these gravity waves in the core of the star. And looking at those waves and comparing two different stars, what we find in this case from Kepler observations is that these groups look different in these different stars, in these two stars. The spacing is bigger in this group down here than in the group up here. And the reason for that is that in this case we have a star that has a hydrogen shell burning, and down here we have a star with a helium burning core. So what we're doing here is that we're looking at two red giants. They look the same on the surface. They have the same temperature, more or less. They have the same luminosity, but in the deep interior they look vastly different. And by looking at these oscillations, we can see the difference between these two groups of stars. And then we can try to understand what's going on in this helium burning phase. And we can do that for large groups of stars. This is a sample of stars plotted in terms of the spacing of the peaks in the gravity wave regime and the spacing of the acoustic modes. And we see a sampling of stars that are hydrogen shell burning, and then we see the stars that are core helium burning. And we can then move on and to also determine the rotation of the stars, and because the rotation causes a splitting of the frequencies. And from that we can then characterize the internal rotation behavior of these stars. And again, we are looking at the surface of stars, but we can see how the stars rotate in the interior. We can see that the core rotates more rapidly than the surface, but we can also see that the core rotates more slowly than these are the observations. And this is what the models would predict the core to rotate. So again, we don't understand what's going on. We don't know why the core doesn't rotate as quickly as the model predicts. And again, we need help to sort that out. And then we can even move further along and see that the splitting is not uniform as you expect if the star is just caused by rotation. It's skewed. And that skewness is caused by magnetic fields in the core of the star. So we can also measure that these red giants have core magnetic fields in their interiors. And this is something that happened in the last few years. So we have now measurements of magnetic fields in the cores of a sample of red giant stars, shown here against the mass of the star. We can see the starts for stars with masses around one solar mass and then moves up. And so this is really where we are now, the frontier, to understand why we have these magnetic fields, what effect they have on the interior properties of the star. And to carry on this work, we have the next step, which has already been mentioned this morning. We have the ESA Plato mission, which is scheduled to be launched in a year and a half, at the end of next year, to carry on the observations and improving on the observations by Kepler, continuing the determination of exoplanets, of course, but also making really advances in the study of stellar interiors using helio and astroseismology. So I'm an old man, retired some years ago, but I really need to keep in shape for a few more years so I can benefit from the wonderful data from this wonderful new mission and continue research in this wonderful area of studies. So thank you very much for your attention.
Let me see. Do I need to switch this? No, you can hear me. Excellent. So questions, please. Come on. If I don't see you and you have your hand raised, jump. Over there.
You mentioned briefly that the spectrum was known better than we know the gravitational constant. So this is a question about the gravitational constant. Many years ago, you wrote a paper about measuring the gravitational constant using helioseismic models. I haven't seen anybody actually try to do it. But is it something you'd suggest to a young scientist now? Because measuring the gravitational constant better than it's done is still, even with the new technologies of cold atoms and so on, it's still a challenge. Is this something you'd suggest to an early career scientist now to measure the gravitational constant?
Well, no, we have looked at it actually. But the point is that what the oscillations, or what solar evolution depends on, is the mass. So the uncertainty in the gravitational constant translates into an uncertainty in the knowledge about the solar mass. We know the product, of course, very well, the product of the gravitational constant and solar mass. And much of what we do, actually, it depends on that combination. Where the gravitational constant would come in would be in the variation in with mass in the solar interior. And I don't think the precision is quite high enough to provide additional constraints of gravitational constants from that. So this is still something we can't do, unfortunately. The point of the comparison is that the gravitational constant would then be one of the uncertainties in our analysis of these data. Because, of course, when we want to learn about the physics of the solar interior, that also depends on knowing the mass of the sun. And so the uncertainty in the gravitational constant actually also affects how well we can determine the equation state of the solar interior. And so I would turn it around and say that please give us a better measure of the gravitational constant. And then we can make even better use of the helioseismic data.
Okay, thank you. I saw there was another hand. Quick, Flores, please.
Very quick. Beautiful review, many thanks. I was wondering if this technique could be extended to low-mass stars also, or even exoplanets. Gaseous exoplanets, that is.
Yes. Low-mass stars, yes. But not very low-mass stars. And that, again, is the result of the way the waves are analyzed, excited. You need this vigorous convection near the surface. So, and if you move down to, well, we have seen oscillations like this in a late K star. We would love to go down to M stars because that's where we see many of the exoplanets. But there we have not been able to do that so far. There have been some studies of oscillations excited in a different way in M stars, but it is nothing definitive. For planets, yes, there are some indications of oscillations in Jupiter and Saturn. They haven't been studied in great detail yet, and I haven't followed carefully. But they are there, and we should be able to use them to learn about the interior of the giant planets. Of course, oscillations of an exoplanet would be something else. That's going to take a while.
Okay, since we're running out of time. Okay, I'll allow this one because I saw you just when I was about to say we have to be done, but that's the last one.
So I was surprised that, thank you for your talk. First, I was surprised that you mentioned magnetic fields before you mentioned differential rotation. Is differential rotation in these objects something which is in your standard model and you manage to do everything related to that and it doesn't influence any more your results?
Please come and help us with all these questions. The reason I mentioned rotation first was that was observed first. It's clear that there's a very strong relation between magnetic fields and rotation. And the fact that we see rotation in the cores of these red giants that's slower than what you model could very well be caused by the effects of magnetic fields. That's modeling indicates that might be part of the reason at least. And also rotation probably is behind the creation of the field, but the most likely origin of the field we see in the red giants is a fossil field made in convective cores on the main sequence. But there's a very strong coupling between all these issues. And so we have to rethink our whole modeling of stellar evolution now in the light of these data, where we now know that rotation and magnetic fields are important to the evolution of the stars. And that's something we're just starting to do now. So yes, this is where we need the young people. Far too complicated for me.
Okay, well, thank you very much. We'll have to go on. Let's thank Professor Christensen again. Yes. And I'll have your medal.
Thank you.
And I'll pass on the microphone.
Hi. Our next plenary speaker is Volker Springel, who is from the Max Planck Institute of Astrophysics. And he'll be talking to us about supercomputer simulations of the universe. And so, Volker, I'll leave it to you.
Yeah, thanks for having me. This is a great honor and especially lovely to be in a full lecture hall. Haven't had this for a while, so it's a pleasure. And I would like to give you some perspectives on my area of research, which lies in structure formation, cosmological structure formation. I'm addressing this from a theoretical perspective. And I would like to convince you that besides the beautiful observations we already heard about this morning and we'll hear a lot more about this week, of course, theoretical work is also critically important to interpret what we actually see. And we have a good model of the universe. It all started in a Big Bang, where the universe is very simple. We have direct observations from this initial state, 380,000 years after Big Bang, when the cosmic microwave radiation was emitted. And at that epoch, as illustrated here in these observations, the universe was very simple. The fluctuations were tiny in the matter radiation soup, and no galaxies, no stars, probably no black holes existed yet, even though the latter is maybe a little bit uncertain. And the observation of microwave background also have established that the universe is made up actually of two rather strange components. At least today, it's dominated by the dark energy component, and 85% of the matter component is a still mysterious dark matter particle. So the standard cosmological model is actually fairly strange, but we have a very good idea about how it started and what the initial state for structure formation was. What we have to fill in is how galaxies came into being, how they formed over time. So actually really completing the whole picture of galaxy formation evolution, that's a task that we face, both from an observation point of view, but also, of course, in theory. Now, in computational structure formation, the idea is that we take the universe as an initial value problem, because in lambda CDM, we precisely know this initial state a few 100,000 years after the Big Bang. Actually, we know it really precisely. We know the matter content, and we know the initial conditions. And then the idea is to evolve this forward in time on a computer to see what that type of model will produce. For that, you have to solve equations, and I just wrote down here the most important systems of equations that you then compute. One is the Polzov-Vlasov system. That's the collisionist-Boltzmann equation governing collisionist dark matter if it's a vanilla WIMP particle that only follows gravitational interactions. You also see the Navier-Stokes equations here. This is sort of for the hydrodynamical flows, the helium and hydrogen gases that are initially diffuse and then under gravity are pulled together to form bound objects. Of course, there are additional partial differential equations you have to address to get the full astrophysics of galaxy formation, in particular radiative effects, radiative transfer, radiative cooling, magnetic fields, eventually chemistry, but then also nuclear astrophysics, because the stellar evolutionary processes themselves, of course, regulating galaxy formation decisively. And then close in to compact objects, you also have to account for effects of general relativity, liberating a lot of energy, in particular when black holes grow. So it's a complicated set of astrophysics, and I will tell you a little bit about how far we've gotten in this program of putting this all essentially on a supercomputer and trying to evolve the universe forward in time. Now, in the dark matter sector, this program has been enormously successful. Already about 20 years ago, it has been understood how cold dark matter clumps and how it's distributed in today's universe. So this is really a prediction that where computer simulations prove to be essential to really see how gravity turns in a nonlinear sharpening process, the initial fluctuations we see in the CMB, into the cosmic large-scale structure on the right, and then also interior to galactic halos, how the dark matter is distributed there. In this big picture on the left, you see the dark matter distribution we expect in a halo of the Milky Way size. So this is 10 to the 12 solar mass in dark matter. But it's not a smooth ball of dark matter. Its phase-based structure is extremely complex. It's rich, it's filled with subhalos. These are structures that have fallen in the hierarchical growth process of this galaxy. And that's basically what we should see if we had dark matter eyes when we look at the galaxy. We would see this ball of dark matter. Unfortunately, it's dark. And we, of course, try to really prove whether this model is correct or not. And we look, for example, for faint signals from weak gravitational lensing and microlensing, but also from things like gamma ray annihilation radiation. Nowadays, I would argue go as far as saying that as far as the dark matter is concerned, the problem is basically solved. With computation techniques, we can nowadays solve the whole spectrum of all the dark matter structures that we would expect, down to the smallest ones we think there should be there, actually bound structures of Earth mass. That's roughly expected in a typical WIMP scenario, a weakly interactive massive particle, where there's a certain thermal limit, particles about 100 GeV in mass, they would have a thermal limit where Earth mass would be the smallest dark matter structure. And so we can devise simulation campaigns that simulate all the structures from rich galaxy clusters down to the Earth mass objects over 30 orders of magnitude in mass. And all the groups doing this basically agree on the outcome of these simulations. That is something that is numerically under control and relatively well understood. Problem, of course, is the universe is, the interesting part is in the baryonic sector, in helium-hydrogen gas, and then in the galaxies that grew out of it. And here also, in the last 10 years or so, the field has made enormous progress in producing stunningly successful simulations of galaxy formation directly out of the initial conditions left behind by the Big Bang. Here you see a compilation of various such simulation projects. Many have probably familiar names. Two primary techniques are used here. On the left, you see so-called zoom calculations where the computational effort is concentrated in single objects. So you get higher resolution there, but you can't study full populations of galaxies. Or one uses so-called box simulations here on the right, some of the famous names from recent years in the field of computational structure formation. And several groups are doing this and reaching quite some success. In these boxes, you simulate a representative piece of the universe, and then you get predictions for tens of thousands to millions of galaxies, and you can compare, of course, to observed galaxy catalogs, whether the properties of these objects are right or not. I'm showing you a few results from a project I've been myself very tightly involved with, the Elastis TNG simulations, now from a few years back. Here we simulated 3 different periodic volumes. You see TNG 50, TNG 100, and 300, from 50 megaparsec to 300 megaparsec, each containing about 10 billion resolution elements in the baryons and the same number in the dark matter. The reason why we do these different boxes is to enlarge the dynamic range that we can cover. These small volumes here, they have better resolution, but they will never contain a very rare object in the universe, let's say a large galaxy cluster, because they're simply having mean distances far larger than 50 megaparsecs. So to see these small, so these rare objects, you have to turn to larger volumes, and then there you have lower resolution. So I come later to this problem imposed by this limit or the competition between volume that you can study in the universe and the resolution we can afford. But first, let's maybe look at, and this is unfortunately not working. Movie is not working, but let's see, try once more. Yeah, it's not working. Is it? Oh, oh, it is. It's not working here on the screen. Is it there working? No, it's because it cycles through Zoom. That's why it's not playing well. Okay, never mind. Would have been a nice movie, but you see only still frames. Yeah, but maybe I'm just, what I meant to show with this is actually what, if that was playing smoothly, but it's not cycling through Zoom, then you would actually see the turbulent structure of the gas in this protocluster region, how it's coming together. Particularly, we would discover that there are occasionally black holes accreting and producing large-scale outflows. Now it's running a bit, that's nice. Let's see whether, yeah, here for example, there is a galaxy coming here from the right and it's producing a large-scale outflow. And that's actually illustrating a problem that is quite acute in these calculations. You have a coupling of small-scale physics and very large-scale phenomena. And for black holes, this is most acute. Black holes themselves are still tiny on the scale of galaxy clusters. Here, by the way, you see the stars falling together to build up the galaxy cluster that's shown here. It's a small part of the TNG50 calculation. And two different physical fields have been shown here, the gas velocity field and now the stellar distribution. I think what you can appreciate is, of course, already from this small illustration is how rich these calculations are. And the dynamics, of course, that are followed here, processes that take billions of years are running here in a few seconds. And we see the full time evolution, something that unfortunately the universe is not kindly showing to us in that way, right? We have to piece it together from observations at different epochs. Now, simulations like this Elastis TNG then produce hundreds of thousands of galaxies. Here are a few selected ones. This galaxy is the gas distribution phase and edge on, and here the stellar distributions. Here's a galaxy cluster, and here's a higher resolution excision from TNG50. And already from this picture, you see, oh, they actually kind of look like galaxies, what we produce. And indeed, of course, this is what one then needs to make more quantitative. The galaxy populations predicted by these cosmological simulations then can be compared in many, many different ways to observational data. One of the most basic things is you compare sizes, say, of early and late type galaxies. And the reassuring thing is this comparison works out extremely well. I mean, not perfectly, but very encouragingly well. So the galaxies the simulations make have the right sizes. This comes about because of the angular momentum that's imprinted on the dark matter halo. It's just the right amount to give us the right galaxy sizes. Here are color distributions. That's much more interesting because there's a red sequence that emerges for massive galaxies, and that has to do with the quenching phenomenon that large galaxies stop forming stars. And this is coming about from the physics of supermassive black hole accretion in our simulations. The galaxies are also distributed at the right places in the universe. We see this from clustering analysis, for example, and also at least the massive black holes follow the scaling relations that we see in galaxy populations. And then you can query these calculations in many different ways. Here's just an example for the gas metallicity profiles in galaxy clusters, where there are differences between cool core and non-cool core clusters, roughly in agreement with observations. You also see how the late accretion, the late enrichment with type 1a supernova with time changes the iron fraction you have in this metallicity compared to the prompt enrichment with core collapse supernovae. And all of this can, of course, be compared to observations. Sometimes you also can make nice predictions. Here, for example, is an example. This galaxy is seen face on. They drive galactic winds and outflows in a bimodal way. Turns out they are more enriched than the rest of the CGM gas. And so there's a prediction here that as a function of angle to the plane of the disk galaxy, the metallicity in the circumgalactic medium should vary. And this is here a result that I find quite nice because it agrees actually between our modeling technique, Elastis TNG, and the EAGLE simulation, which uses different simulation code and also different approximations to some of the physics of galaxy formation. Yet the prediction is roughly the same. And so when you have that, then we think as simulators that this is probably has a chance to be really robust and is not overly sensitive to some of the modeling uncertainties. The simulations are also good enough to do galactic dynamics nowadays. Here you see a few examples of Milky Way-sized galaxies, the stellar disks, and some of them make, for example, bars and spiral arms, and there are a lot of people interested in galactic dynamics. Nowadays we have enough particles in these simulations so that these calculations are not dominated anymore by noise, but are reflecting real galactical dynamic processes, even though they are carried out in full cosmological context. Because these simulations are quite rich in the phenomena they can simulate and they predict, the data, I would argue, is of quite unique utility for the whole field. We have made our simulation data publicly available, and the uptake in the field has really been enormous. Colleagues, some of them might be in the room, have used our simulations to write papers, and for elastocene G, more than 1,100 papers have already been written over just the past 6 or 7 years. So we are quite, of course, stunned by that, and we think that means that hopefully going forward, that future simulations efforts will advance the field and the theoretical understanding of what we actually observe even more. But let me take now a step back and critically discuss a little bit what's actually entering these simulations and what we maybe have to do in the future to get better ones. So the basics is that you compute the gravitationally driven dynamics of dark matter, so collisionless dark matter. I've argued this is something we understand very well. We can also do numerically with very small residual uncertainty. Then there's ideal hydrodynamics. This is not quite so easy, but still possible to control the errors. At least we can have a good understanding of what the limitations are there. And we can also set up the initial conditions basically perfectly accurately, at least as far as lambda CDM cosmogony is concerned. So that part is very, very well understood. But in addition, we have to add astrophysical processes, and that starts with gas cooling of diffuse gas. Then gas settles into a multi-phase interstellar medium, undergoes star formation there. The stars evolve. This is a subgrid model for these cosmological simulations. The stellar astrophysics is basically included here as a subgrid model, but we need to assume, of course, and take results from our colleagues in stellar astrophysics on how much energy, for example, is liberated in a stellar explosion, how long that takes before a star explodes, and so on. That's all in this box here, stellar feedback. Also, they, of course, release heavy elements to the diffuse gas, which are then recycled later on. The other big player are supermassive black holes and their growth, giving rise to black hole feedback. In large galaxies, we know that this is probably the process responsible for quenching the galaxies. We model this in our simulations, but it's uncertain how precisely this is done. We also need to model radiative fields in a very approximate way. And then there are non-thermal components, magnetic fields, and in particular cosmic rays, which are sort of always the elephant in the room because they are often not well understood. Now there's also a color key here. So green kind of means these are the areas I would argue we have relatively small uncertainties how to do that. Yellow is kind of doable, it's a bit harder, but the red is where the real problems lie. So there are the systematic uncertainties are very, very large at this point. Therefore, based on that, there's really a small-scale frontier we are working on in the field. So we are pushing now the resolution of these simulations to much better mass resolutions. The fiducial goal is sort of reach 1 solar mass resolution in a Milky Way-sized galaxy. That would allow us to basically represent every star with their correct mass. We want to clarify the physics of galactic outflows. These are critically important to reconcile sort of the halo mass function in a lambda CDM cosmology with the faint end of the galaxy luminosity function without these galactic winds that are assumed to be very strong in our simulations. That's not really possible. Then, of course, the black hole physics, I mentioned this already, is super important, even harder than the galactic wind problem. dust we would like to have as well. And we would like to follow the orbits of black holes better, because there is, of course, an important opportunity to predict event rates for supermassive black hole mergers that will be found with the LISA observatory in maybe 10 or 15 years from now. So we want to have theoretical predictions for that are robust and reliable. So that I would call the small-scale frontier. But there's also a large-scale frontier, because for the large, ambitious mega galaxy surveys that are now underway and producing first results, Euclid, Rubin, and Roman, and so on, observing billions of galaxies. These surveys, of course, they try to detect cracks in our understanding of cosmology in lambda CDM by measuring galaxy clustering especially, and measuring weak gravitation lensing super accurately. We need equally accurate theoretical predictions, it turns out, to really put the potential of this data to its full use. And so that calls for equally large cosmological simulations, basically of gigaparsec size, with trillions of particles. And the field is trying to do this, but if you look at TNG 300 megaparsec is a far cry from this, right? This is a volume that's 1,000 times too small. Question is what to do about this. So recently we've made one first effort in this direction, which is our Millennium TNG simulation project. The idea basically was to couple the illustrious TNG approach, a full hydrodynamical simulation of galaxy formation, with the older volume of our quite successful Millennium simulation from 20 years ago, so which at that time already had 15 times the volume of illustrious TNG. So for the moment, and that's sort of possible with the progress we've made in computational techniques, we can produce a hydrodynamical simulation now of the size of Millennium, including the physics of illustrious TNG. So that's what we've done. But then we've also run a dark matter only twin version of that. And then we can compare basically every halo, the hydrodynamic version and the dark matter only version, and understand how galaxies populate the dark matter halos in detail. And with this learned understanding, we can then run a much larger hydrodynamical simulation, Millennium TNG XXL, with 3 gigaparsec on a side. That's then indeed 1,000 times larger than TNG 300, and yet can make accurate galaxy clustering predictions for that calculation. And just briefly going through a few of these things. So in the hydro simulation, we also have changed to an outputting directly on the pass-backwards light cone of a fiducial observer. That's basically only what you can observe, of course, in the real universe. And for the simulations being that big, it doesn't make sense anymore to look at time slices, which are fundamentally unobservable in that way, but rather continuously output the data. And if you do this, you can then produce mock observations that are really fully realistic. Here, for example, is the Sunyaev-Saltovich piece of a light cone 10 degrees on the sky, and here's a galaxy cluster enlarged. And with this technique, you then can see that the foregrounds and backgrounds actually induce a very significant contribution in the outskirts of the galaxy cluster. So the profile of your Sunyaev-Saltovich comptonization would look completely different if you just excised this cluster, even with 200 megaparsec around it from a box, and looked at it. You get this deeply falling thing, while with all the foregrounds, you have a much higher signal in the outskirts. So that needs to be properly understood, of course, to interpret observations. With these hydro simulations, you can also really mock catalogs and look at data in an apples-to-apples comparison. Here's, for example, a galaxy cluster richness comparison relative to the comptonization, where our simulations, Millennium TNG, are compared to the Planck-Red-Mapper combination, and the agreement, it works out pretty well. There's a small offset in the cluster masses of about 0.2 dex, which is still unclear where this comes from, and we of course blame the data, but maybe it's our simulation. But still, you can make increasingly sophisticated mock observations, and I think that's generally speaking a way to do this more in the future. Then since having these light cones, we can also, make mock galaxy surveys, of course. Here is, for example, a galaxy, it's a galaxy light cone to redshift 2. We would look here in the center, we would be here in the center and look out about 5,500 megaparsec. to redshift 2, and the galaxies thin out here at the edge because they partially haven't formed yet, and you can only look at the most massive ones. And of course, it's then easy in the simulation model to include the redshift space distortions. So you see here the strong finger of God effects in the clusters pointing to you, and on large scale, the Kaiser squashing effects. And when you then have the galaxies on the light cone in a realistic way, in a magnitude limited survey, you can then look at galaxy clustering, for example, in redshift space, compared to the extremely accurate SDSS data on the monopole, quadrupole, hexapole moment. Agreement between the simulation and the data is fairly good at this point. So we need to concentrate on the small deviations, which are at the percent level. And they contain some of the interesting signals. One of them is, for example, the neutrino impact on meta-clustering. So that we had included also in our new simulations. Neutrinos, for typical numbers of the summed rest mass, about 100 millielectron volt, they make up about 1% of the dark matter. So the real universe is hence not only filled with dark matter, we have about 1% of hot dark matter admixture. And the neutrinos, being quite realistic still at high redshift, they slow down due to cosmic expansion, and then at late times respond to the dark matter structures and are bound suddenly by some of the largest galaxy clusters. You see this here. Down here is the dark matter light cone. We are sitting again at the center. Here's redshift 2 on the left and redshift 2 on the right. That's the neutrino density field we predict in these simulations. So, at high redshift, it's still very homogeneous. But then, as the universe expands further, the neutrinos are slowed down and start accumulating in some of the biggest structures and modifying the structure actually on these scales very slightly because they're suddenly slightly more massive because of the neutrino mass. And these weak effects can be detected likely with the future galaxy surveys. So that's an important goal, of course, of fundamental physics to provide more accurate large-scale structure constraint on neutrino masses. And where this comes in is also for weak gravitational lensing, which is one of the primary techniques that are foreseen for these mega surveys. We can make very accurate predictions for the deflection angle maps, and then work out, for example, how this is modified by things like AGN impact, right? And that we see here. And also the intrinsic alignment of galaxies. I see I'm drawn off stage in a second. Let me just maybe point out that, of course, the high redshift arena, I'd say, with JWST is also very exciting. So we reproduce the UV luminosity function with these type of simulations down to up to redshift about 10. But for some of the very massive galaxies, redshift 12 to 14, there's definitely an under-prediction in this type of galaxy formation physics model. And to close off, I just want to say that we, of course, have to work on the numerical techniques as well. There, the prospect is not as bright as you might think, because the hardware is now all going to AI and GPUs, and only those become any faster. So, for example, double precision is now removed by NVIDIA in the newest generation of GPUs. This is not good for the type of work I'm representing. So we'll see how this pans out in the future. And, our codes get more complex, and if there are young people here in the field, I'd encourage them to not give up. So now, when I was a student, I had to deal with this thing, a few thousand lines of code. Now my new students have to do with 500,000 lines of code, and they tend to run away when they get this number. But I think there's no reason to be scared. I think this field still is very exciting, and I hope you, and we need certainly help to make use of all these fantastic computers for making even better predictions in the future. Thanks.
All right, we have time for at least a couple questions. Any questions from the audience? Oh, well, I saw you over there and someone over here as well.
Yep, thank you very much. Excellent talk, Volker, as usual. So I just want to get a small piece of your talk about the triple black holes, which you mentioned as one of a problem. So what do you think, what we need? Better resolution, better physics?
So for the triple black hole, yeah, their resolution is a key. So
Key.
you can the dynamical friction for the black holes, how they sink in galaxies. Actually, behind you, Anna Genina has made progress on this. How you model the dynamical friction to bring black holes together. There's still the last parsec problem is very hard. You need to do n-body dynamics. There are techniques developed by people right now for that. So I think this is with a lot of additional work in the next years, we will see a lot of progress there.
Yeah, probably regularization as usually with algorithmic regularization or whatever which we can include it.
Exactly. Yeah.
Yep. Thank you.
Question over here.
Thank you very much for the fantastic talk. I was wondering, in fact, in terms of the simulations work really in conjunction with observations and the calibration of them. I mean, you showed how important it is to have data, in particular galaxy properties, etc. What are the observables on the gas at high scale, at large scales, and the gas in galaxy clusters that we need or would be useful in order to help calibrating or help to improve even more the simulations?
So yeah, I think there's several. I mean, there's, for example, at very high redshift, there's things like 21 centimeter cosmology, so around reionization. Then you have, of course, absorption line studies. So any information, X-ray, also SZ, kinetic SZ. So the diffuse gas is particularly interesting because there, I would argue the simulation uncertainties are less strong. In principle, we should be able to simulate diffuse gas much better than the very dense gas in the interstellar medium. So I think there are many observation probes, absorption line diagnostics, also Lyman alpha and so on. That's, we are at the beginning of really fully exploiting this.
Thank you so much.
Okay, maybe one more. I think we have one more speaker, so maybe one more question while the... No, we don't have... Do we not have another speaker? We do, yeah. So maybe while the speaker comes up, we can have one more question for Volker.
Yes. Thank you for the very nice talk. I have two questions, very short ones. Do simulations reproduce the distribution of very large mass clusters we see in observations? And what about the distribution of superclusters in simulations?
Sorry, I didn't get the last. Can you repeat?
The distribution of superclusters in simulations, large simulations.
The large clusters and superclusters. So you mean the really, in the cosmic large scale structure, the biggest things, right?
Yes.
Yeah, so with our newest simulation that we haven't actually done a proper assessment of that. My default answer would be we see things like the Sloan Great Wall and so on. I don't think there is a discrepancy in the largest structures. That at least would be my statement here.
Thank you.
All right, thanks a lot, Volker. Give him one more round of applause. And our final plenary speaker of the day is Maria van der Zaan. I hope I said that okay. Who'll be talking about the chemical complexity around evolved stars. So take it away.
Yeah, thank you. And first of all, I'd like to thank the organizers. It's really a great honor to talk about the chemistry around evolved stars here during a plenary talk. And I'm happy that you're staying around. I know we're delayed, and I'll promise to not go over time. So chemistry happens throughout the life cycle of a galaxy. You find molecules in clouds in the interstellar media, around protostars, and also around these evolved stars as well. And the field of astrochemistry studies these molecules. And it we don't just determine which molecules are present where, but we also look at the formation and destruction processes, because these molecules are very sensitive probes to the physical conditions of the environment in which they're found. Because for a specific molecule to be able to exist, you need to have a certain density, certain temperature, certain radiation fields. So by studying these small molecules, we can actually understand the structure, dynamics, and evolution of these large astrophysical environments in which they're found. Now, most of astrochemical research focuses on star and planet formation, so the molecules that are present in these clouds in the interstellar medium, and as we go through protostars with protoplanetary disks, and then finally a planetary system surrounding them. And also it follows the molecular journey from cloud to planet. And with this presentation, I'd like to emphasize the importance of evolved stars, because it's during the death throes of dying stars that the interstellar medium is seeded with the building blocks for the next generation and of stars and planets to form. And in particular, I'll talk about asymptotic giant branch, or AGB stars. And the AGB phase is one of the final evolutionary stages in the lives of stars with an initial mass between 0.8 or 8 solar masses. So this is the majority of the stars and also includes our own sun. And the AGB phase is characterized by mass loss. These stars lose their outer layers by means of a stellar outflow or a stellar wind. And this wind is thought to be launched by a two-step mechanism where pulsations of the star itself facilitate dust formation, which then drives a dust-driven wind, stripping the star of its outer layers. And it's very efficient at doing so. AGB stars have mass loss rates between 10 to the minus 8 and 10 to the minus 4 solar masses per year. And that's a lot. In fact, it's so much that it's a process of mass loss that determines a subsequent stellar evolution and not a nucleosynthesis in the core. And thanks to their outflows, AGB stars are important contributors to the chemical enrichment of the interstellar medium. About 80% of the gas and 35% of total dust is thought to originate from these stars. And if you look at just newly formed stellar dust, they can contribute up to 70% in galaxies like our Milky Way. So let's take a closer look at an AGB star and more specifically its outflow. So in this illustration here on the left, you have an AGB star. And the outflow can be divided into three main regions, and each is characterized by specific chemical and dynamical processes that are tightly coupled. So in the inner winds, the chemistry is taken out of equilibrium because of shocks caused by stellar pulsations. Then a bit further out, dust is able to condense from the gas phase, and this is the region where the outflow is launched and material gets accelerated away from the star. And then finally, in the outer winds, this material reaches its terminal velocity, which is somewhere between 5 and 25 kilometers per second, so not too fast. And the chemistry in this region is mainly photochemistry. Because of the lower density, the interstellar UV photons can more easily penetrate this region and create a very reactive soup of atoms, ions, and molecules. Now, the type of chemistry in the outflow all depends on the elemental carbon-to-oxygen ratio of the star itself. And this is because of the strong molecular bond of the carbon monoxide molecules, so CO. If you put carbon and oxygen together, they really want to form carbon monoxide. Now, all stars start out as oxygen-rich, so C/O ratio smaller than 1. And in that case, you will have an oxygen-rich outflow, and the types of dust that you form are silicates and metal oxides. Now, during the AGB, the star undergoes a process called a dredge-up, and with each dredge-up, newly formed carbon is brought up from the stellar core up to the stellar surface, so slowly increasing the C/O ratio. And after a while, you might have a C/O ratio larger than 1, so you'll become carbon-rich. The type of dust that you form is like amorphous carbon and silicon carbides. So the type of chemistry in the outflow depends on the star's age, but also on its initial mass. Not all stars will become carbon-rich. For example, our sun is not massive enough to become carbon-rich and will remain oxygen-rich. Now, I'd like to point out a few things. So AGB stars are quite large, of course not as large as a galaxy simulation, but still the stellar radius is about 1 AU, and the outflow goes from the stellar surface to some 20,000 stellar radii or 20,000 AU. So these are big stars surrounded by even larger outflows. And because we have an outflow, we've got these large gradients in density and temperature. We go from 10 to the 13 particles per cubic centimeter in the inner winds at a few thousand Kelvin to less than 10 particles per cubic centimeter at a few 10 Kelvin where the outflow merges with the ISM. And it's because we've got these large gradients that we have this rich diversity in chemistry, that we have these three distinct chemical regions which include dust formation. Because it's quite difficult to form dust, we have to do a state change. We go from the gas phase to the solid states, and that's quite difficult to do if you're in space. But the AGB outflows are one of the few places where this phase transition can efficiently happen, and they are real dust factories. Now, not only a lot of dust is being formed, there's also a lot of molecular richness, so more than 100 molecules have been detected so far. I'm not going to go over this, but it's a lot of molecules that we see here. And when it comes to chemical modeling of AGB outflows, we can again distinguish three main categories. We've got models that are geared towards the non-equilibrium aspect of the chemistry in the inner winds. Then you've got sort of the more classical chemical model, which is a gas phase only chemical kinetics model that describes the chemistry in the outer winds. And you can extend this model by including dust gas chemistry as well. Now, the story that I've been telling so far is relatively spherically symmetric. So we've got a nice star blowing a nice bubble, but of course life isn't easy. And we have these large-scale asymmetries present throughout an outflow. So this is a wonderful example of a spiral around R Sculptoris. This is CO emission as observed by ALMA. So this is definitely not a nice bubble. And I'm part of the ALMA large program Atomium, and this is our postcard. So we observed 12 oxygen-rich AGB stars. This is again CO. The red is moving away from us, the blue towards us. And none of these outflows are spherically symmetric. Some a bit more so than others, but in general, they're all a bit of a mess. So yeah, there's a lot of structure going on over there. And we think that these large-scale structures are caused by binary interaction with either a stellar or a substellar companion. So that's a massive planetary companion or a brown dwarf. But we also have to deal with small-scale asymmetries quite close to the star. And this is because of the convective nature of the outer envelope. And here you see a simulation of an AGB star. You've got these huge convective bubbles moving material up and down and just being very mesmerizing. But what's perhaps even more mesmerizing are these recent observations, again done by ALMA and by the team of Wouter Vlemmings, where you can see convective motion on the surface of an AGB star. So here you have the surface of R Doradus observed over the space of a month. It's going to loop through again. So we've got these nice bubbles moving along the surface. So that's really quite amazing. And these small-scale asymmetries also impact the chemistry close to the star, and this is something that we see in different molecules being present in different regions close to IRC 10^16. So you see that the bubbles sort of impact the inner wind as well. So AGB stars, well, their outflows are chemically very rich and also quite complicated. And I'd like to use the rest of my presentation to talk about how chemistry can help us understand both the driving mechanism of the outflow as well as a shaping mechanism. So for the driving mechanism, I'll talk about dust formation, and I'll then move on to companion-induced structures, and I'll end by talking about a specific structure, namely that of a disk. So let's start with dust formation. And I think that understanding the stellar evolution of these low to intermediate mass stars is a chemical question, because this mass loss is driven by a dust-driven wind. And forming dust is a fundamentally chemical problem. And we still don't understand exactly how dust is being formed. We know that it's a chemical kinetic process where monomers, gas phase monomers, react and form larger gas phase clusters until this cluster condenses into a solid state seed particle, which then grows via accretion. But we don't really know which monomers we should be looking at, especially for oxygen-rich stars. And then exactly how you make these bigger clusters is also quite unknown, because you can't treat a large gas phase cluster as a small part of a solid-state dust grain. So there's a lot of open questions there, and this has far-reaching repercussions, because if we don't know how dust is being formed, we don't know how the outflowing is being launched. So what are the evolutionary timescales? And we also don't know exactly what type of dust is being formed, with which grain size distribution. So this feeds then into the ISM. All these uncertainties will get propagated along. And there are two ways in which we can study dust formation. So if you have an ERC synergy grant, like the Nano Cosmos team, you can actually build a outflow in a tube, so that's the Stardust machine, where they're able to mimic a carbon-rich outflow all the way from the stellar surface to where the dust will reach the ISM. And one of their results, they found that if you create a more realistic environment, so by increasing the amount of C2H2, which is abundantly present around the carbon-rich star, you see that not only does the number of dust grains produced increase, but also their grain size distribution changes, and they go from being relatively spherical to, well, these, well, quite oddly shaped guys as well. So that's something that we can do for carbon-rich outflows. For oxygen-rich outflows, such a machine doesn't exist, and we have to look at observations and theory. So we can use ALMA again to look at the inner rings of certain stars, and this is an example of ALCL and ALF around W Aquila. And we think that these molecules should go into dust because there's aluminium in there, so it might go into dust. And also, if you look at the spatial distribution of these molecules, they're present only very close to the star, and then they disappear. And this is too close to the star for the molecules to be photodissociated by the external UV fields. So you go from the gas phase, you disappear, we assume that you go into a solid state dust grain. And I'm not going to show my chemical model results because I tried to reproduce these radial distributions and we failed. And that's because we're missing chemistry. We don't have all these reactions available where we can go from gas phase molecules to solid state particles. And what you do then is you go to a friendly theoretical chemist and you ask for them to please calculate all these clustering reactions. And this takes quite a lot of time. Here we've got a few examples of aluminium oxide and calcium titanate, but then we can sort of converge, hopefully, on a dust formation network. So dust formation, understanding dust formation is a very interdisciplinary and fundamentally astrochemical problem because we are combining observations with theoretical modeling as well as laboratory and experimental chemistry. And once we figure out dust formation, we can finally have a chemical model that covers the entire outflow and really understand exactly how AGB stars die. Now, let's move on to these companion-induced structures. So most AGB stars have a companion, and this companion can create a very nice and intricate structure throughout the outflow. But it's quite difficult to find these companions because AGB stars are very bright, and also they produce all this dust, so they obscure whatever's going on inside the outflow. But if the companion is a star, it will have its own UV radiation fields, and we can then identify chemical traces of hidden stellar companions. And this is, for example, done for IRC 10-16, where HC3N was found to be very abundant, well, relatively abundantly present, very close to the surface. And this HC3N is a tracer of a solar-like companion, and we know that IRC 10-16 should have some sort of a companion because there's spirals in its outflow, and these chemical models now suggest that it could be a solar-like companion. But even if we already know that there's a companion, such as for W Aquila, we can still use chemistry to constrain the orbits of these binary parameters. So here we have SIN, a moment zero emission around W Aquila, which is the red star, and the yellow star is the current position of its solar-like binary. So SIN is present very close to the star, which is something that you would expect if you got a solar-like companion, but what you don't expect is that it's only present in a wedge throughout the outflow. And if you then look at a PV diagram, you see that there's this beautiful arc. So my colleague Daisa Danilovic interpreted these observations as traces of a highly eccentric orbit. And she devised an astrochemistry-based method to constrain the orbital parameters. So using observations, astrochemical model results, as well as hydrodynamical models. And this also is like a first limitation of the current chemical models because they're all one-dimensional and these outflows are clearly three-dimensional. So we need to move towards a 3D chemical model, especially if you want to keep comparing hydrodynamical models to observations. Because these hydrodynamical models give density as an output. And if we want to compare them to observations, we need chemistry to translate density to molecular abundances, so we can then create a synthetic observable. And at the moment, this is only possible for CO, so this is what we did for W Aquila, because CO is quite a simple chemistry. But for all the other molecules, we need to calculate a chemical reaction network. And as long as we don't do this, we are missing out on already available information, because we already have all these ALMA observations of all these molecules. And as long as we don't have such a 3D hydrochemical model, we can't bridge the gap between theory and observations. Now, just to plug chemistry into a hydrodynamical model, that's computationally not feasible. That would make it run for far too long. And a promising way to speed up these calculations is by using machine learning. So if we emulate rather than calculate the chemistry, we can considerably speed up this part of the calculation and perhaps finally get a 3D hydrochemical model. And this emulation is being done for a variety of astrochemical environments, including AGB outflows. Now, another thing that we found in the ALMA large program, in the continuum observations, is that there's potentially a second pathway to dust formation. This is all rather tentative. So here we have pi bar GRU, it's a known binary. You've got a companion over here, and you see this plume of, well, let's say dust moving away from the binary. So perhaps dust could be formed not just in the shocks caused by stellar pulsations, but also in the shocks caused by the companion as it moves through the outflow, so companion-induced dust formation. And this could increase the amount of dust being formed by AGB stars, so increase the output to the interstellar medium, and also, depending on where the dust is being formed, this could also affect the mass loss rates of these stars. So this is quite a new result and, well, still TBD. Now, let's end by talking about a specific structure, namely that of a disk. And the disk around L2 Puppis is the most nicely observed disk around an AGB star because it's very close by. And this is an image in the optical taken by SPHERE. So this dark band that you see is an edge-on dusty disk. And then the two cones of light being scattered off this dusty disk. If you then look at it with ALMA, you see that there's a blob. And this blob also moves. So this is a tentative planet detection of a planet of about 1 Jupiter mass size. And L2 Puppis used to have the same initial mass as our Sun, and we also have a Jupiter mass planet orbiting around us. So this could be a sneak peek into the fate of our solar system. Now, this disk is very similar to protoplanetary disks in structure, so disks around young stars. So it's got a relatively similar density and temperature structure. It's just smaller and much warmer. And if you're then more chemically inclined like I am, you want to create a chemical model. And for that, you use a model of a protoplanetary disk and you feed it the conditions of this L2 Puppis disk. And we find a variety of interesting chemical results, but I'd like to highlight that complex organic molecules can also be formed quite abundantly in the midplane. So we've got methanol and methyl formate, I think. They're too long, I don't know their names. And I'm waiting now to download some reduced ALMA observations to see if the chemical model is actually right. So fingers crossed, that would be nice. And we've also got disks around post-AGB stars. So that's the next stage in evolution, where the star has lost most of its outer layer and the white dwarf is sort of peeping through and ionizing the circumstellar material. And if you look at this guy, it's clear that there's some sort of binarity going on. And if you then zoom in with the VLT, you see that there is a circumbinary disk around this post-AGB star and its companion. And again, this disk is similar physically to the disk around L2 Puppis and around protoplanetary disks. So we've got disks all across stellar evolution along surrounding baby stars as well as the elderly stars. And especially these post-AGB circumbinary disks could be sites of second-generation planet formation because you've got these white dwarfs with all these planets orbiting around them that shouldn't really be there. So perhaps they have been formed within this disk. And if you want to study which types of planets are being formed, then we need to do what the protoplanetary disk community is doing and study the chemical composition of these disks. So to conclude, AGB stars are very important contributors to the chemical enrichment of galaxies. Their outflows are rich laboratories with more than 100 different types of molecules detected, and they are sites of dust formation. But we don't know how dust is being formed, so this is a fundamentally chemical problem with impacts on stellar evolution and feedback to the ISM. Large-scale structures are ubiquitous. These are caused by binary interaction, and chemistry can help us reveal hidden companions as well as constrain their orbits. And this really reveals a need for 3D modeling, and then I also briefly touched on this second pathway to dust formation, namely companion-induced dust formation. And disks are present at both ends of stellar evolution, so these could be sites of second-generation planet formation, but for that we again need to look at the chemistry. Thank you for your attention.
A rare talk that's under time. Amazing. So I'll say, yeah. Yeah. Questions for a speaker? Yeah, back there.
Hi, Marie. Thank you for the wonderful presentation. I was wondering also about fourth dimension, which is time, because I think that non-stationary chemistry could be also important, especially with ultraviolet and pulsations or waves. What do you think about this topic?
Yeah, exactly. Yeah, there's the time component. That's something that, well, in a one-dimensional model, it's just a parcel of gas that you follow along. But something that was, wait, I have to click all the way back. But if we look at his ambition around W Aquila, the fact that it's in a wedge clearly indicates that there's a time component. Because SIN was formed during the last periastron passage of the solar-like companion. So SIN was formed, and then it was moving away from the star. And yeah, now the companion is too far away to create SIN. So there's definitely a time component, and for that we would have to couple it somehow to, well, a hydrodynamical simulation, either by post-processing or by coupling it. So yes, definitely there's a time component.
Other questions? Yeah, right there.
Thank you for the nice talk. I have a question. If in the chemistry slide you showed, if the cosmic rays play a role, especially when the aluminium species go out on the dust, freeze out, or if there is desorption by cosmic rays, or
Yeah, so cosmic rays are taken into account, but they don't play such a big role in the outflow because the temperatures there are quite warm. So it's not like a dark cloud where you really need cosmic rays to kickstart all the chemistry, but either you've got a stellar radiation field from a companion and you've got an interstellar one. So they are taken into account. They play some role, but it's quite small compared to other environments. HB stars are quite unique in that aspect as well. Yeah. Okay. But the mid-plane chemistry that we find in the disk around L2 Puppis, that is cosmic ray initiated. So if you have a disk, then again they start to play a role. Yeah.
Okay. Great, thanks.
Right, and because the talk was so short, we have time for other questions too. Yes, right there, please.
Thank you for a wonderful talk. So I'm Anne Andersen, I'm from Copenhagen. I was just wondering, so the disks, is that like a regular evolutionary process of AGB stars, or is it just in binaries? Or because, I mean, from a dust chemistry point of view, it's wonderful. Suddenly you get a whole new pressure density regime and a whole new phase diagram you can work with, right? It makes everything more complicated, but also more prosperous.
Yes, definitely. So you do need a binary to sort of coax the outflow into forming a disk, because otherwise it would just be a nice little bubble. And it depends on the mass of the binary companion as well as the orbital distance. So we think that first you create, oh, what was it? Of course, now I'm blanking, but you go from disk, so you go from a disk to a spiral as the star moves along the AGB outflow. But that's something that hydrodynamical modelers are looking into. But yeah, disks are being formed. We have a few known examples around the AGB stars. So L2 Puppis, of course, because it's just right around the corner at 64 parsec. There's a few other ones, and then there's some 5 or 8 post-AGB circumbinary disks that we know of. And that's definitely something that I'd like to look into from a dust formation perspective and just chemistry. Disks everywhere.
Right, and because I'm cognizant that we're running into the next session, one last question, and then we can move on.
Right. Thank you so very much for a wonderful talk and beautiful overview. So my question is the following. So, every other binary AGB likely has a white dwarf companion because AGB might be the second star in a binary. So the question is, can you easily see chemically the presence of the white dwarf rather than a main sequence star, especially if it's a little bit farther away?
No, so that's also a star that we have taken into account when doing the chemical modeling. So it was a 10,000 Kelvin white dwarf, where we found there is a chemical signature of these stars, but it's not quite as big as that of a solar-like star, because, okay, they're brighter, but they're also smaller. So the geometric dilution plays a role there. So there is still a role. Well, they do have chemical traces, but they're not quite as obvious in the chemistry as solar-like companions. But yeah, there's definitely a range of there's a huge degeneracies, let's put it that way. But yeah, we can find white dwarfs in this way as well.
Thank you.
Let's thank the speaker one last time.